a very simple problem because the force, well, eventually everything matches to this simple equation that displacement of the vortex close to defect is given by pinning force. So this C is effective elasticity, so effective spring constant that other vortices act on the given one. So it's not single one reduced interaction of many vortices with defect with interaction of a single vortex with defect, and this single vortex is in the background of other vortices. And the interesting thing is that the force depends on displacement itself. So it's not the force of the undeformed vortex, which would be here, but it is the force of the vortex which is already displaced, and this is non-linear equation. We can rewrite this force equation through effective pinning potential. So this x plus u, x is position of vortex far away, so plus u is actually this position of the tip of the vortex with respect to the pinning center, and this is effective parabola of interaction of effective cage potential of all other vortices. And if this is effect pinning center, then what we do when we drag vortex lattice through defect, we move this parabola through the defect potential. Now let's see what happens. So we move, and please stop here. Okay, we didn't stop. Let's try again. Okay, let's move. Move, and please move, please. Okay, can you move? Okay, seems that can you go back to the slide? Because neither I can do anything, nor you. Oh, here. Okay, so we move. So that's how potential evolves. Now you see there is another minimum and there is jump. Here we go, yeah, let's continue. So this goes here, this, and then here it will jump. So, and this is energy, how it changed in this process. So when we move, we follow this line, and now here we jump, we continue to move. Then another minima appears. Now it would be good to jump, but we jump only here. So that's how it goes. And if we come to a vortex not head-on, but at some distance, then we get trap, and the average pinning force is given by the jump in energy times trapping distance. So this is for isotropic situation. Why should we do anisotropy? And well, not only because it's beautiful, but also it is actually useful. So if there was very nice work by Elizeldov where they first introduced squid on tip magnetometry, and they look on the pinning of vortices on nanoscale, and they actually found that in order to explain, to fit their data, they have to consider arrangement of 5 pinning centers, and you see this potential is quite anisotropic. So what kind of, to see what's the difference, let's first consider one-dimensional case. in symmetric situation, which was before, so this is this bare pinning, and this is together with elasticity, we call these two branches as a free branches because far away they correspond to a vortex which is far away from defect, so this we call free. Whereas this branch we call pinned because it's localized where the tip is near to the defect. Now when we go to asymmetric situation, so we just make one slope a little bit less. So here is the same steep as here, but the slope a bit less. Now when we put it to this combined equation, then actually the slope is not so steep, then this jump will disappear, and we have two curves. And now which one should we call free, which one pinned? Because this curve asymptotically goes to vortex far away, but this curve also goes to asymptotically far away. There is no distinction between pinned and free branches. So now another thing which we should discuss is that when we have the jump here, the tip of the vortex actually moves, and it goes, so from here, from this point to this point, so all these regions is actually impossible for the tip vortex to visit. It just flies through it, but we cannot stabilize it there. So if we look how effective potential change when we reduce elasticity, then now two states appear, and there is this dotted line piece where the curvature is negative. And here, no matter how you try to tilt this potential, you cannot stabilize the particle. So in 2D, if we change elasticity, then we see that now there is onset of strong pinning, and we have this ring which forms and expands, and that's what happens in isotropic situation. In an isotropic situation, actually something more interesting happens. So now you see it will start from 2 points, and there are these crescents which merge here. So to study it mathematically, we consider this pinning potential, and this is quadratic, this parabola, and we can expand this parabola term which depends on the position of vortex far away. Here quadratic term is irrelevant. We should minimize it with respect to this r tilde which is here, and taking this quadratic plus this, combine it together, we get new pinning potential, and mixed terms gives tilt force. So now the dragging of r corresponding to a tilt of overall potential, and this looks like this potential surface. Now when we tilt it stronger, then this minima disappear, and the particle here will jump, and that's what we have with strong pinning. And this reminds this maze game where actually particle can be stabilized only at a few different points, and otherwise when we tilt it jumps somewhere. So stability of our system, so the position of minima, is determined by the Hessian matrix, which is matrix of second derivative, and the jump appears when the minima goes to a saddle, which means that when determinant of Hessian matrix, so we should take matrix of second derivative, taking this determinant, and when this determinant vanishes for the first time, then we go into, in 1D it's simply when second derivative changes. Now in 2D we should calculate this Hessian determinant, and when it's changed sign, then we get instability. So if lambda minus is the lowest eigenvalue of matrix of second derivative of pinning potential, then adding elasticity here, so this gives us instability criteria which replaces Labusch criteria in isotropic situation. Now, using this machinery, we expand do-Taylor or Landau expansion near to the instability point. This axis of instability we call x, so here the coefficient change sign, and here nothing change sign, and we add, this is tilt, and this is a higher order term. Not all of them we should write, because cubic term and this term, they are not there, because by our definition lambda minus is the lowest eigenvalue. So if we had this or that term, then there would be another point where lambda minus is even lower. So these terms are not written here because they're absent. Now we take matrix of second derivative and calculate determinant. So this would be, this bracket is second derivative over x. This is second derivative over y, and this is mixed derivative square. Looks rather complicated, but we should keep in mind that this is small. We'll look on the regime where kappa m goes to 1, where this goes to 0. So we're looking close to this saddle where all these x and y's are small. So this term goes to 0, but here are quadratic, we should keep them. This is constant term, but these terms are higher order, are small, so we drop it. And here the quadratic term, which we should drop compared to that. Then when we come all this together, we obtain simple quadratic equation which gives us ellipse. So this is ellipse where we have, which starts from the point and then goes to an ellipse. This is jump line, so when we come from here, we jump and we land on another ellipse as it appears, and when we go from here, we add here. So there are these two ellipses, dashed is landing, and this is jump ellipse. They touch each other in 2 points. Here there is no jump, and well, there are some topological arguments that I can tell later if you wish. And as a result of this onset from 0, we have another critical exponent for pinning, not kappa minus 1 square, but either 5/2 or 3, depending on direction of drive. So to see it, we go back from the tip space to asymptotic space. So this is a coordinate of vortex position far away from defect. And then what was ellipse here is some narrow crescent. So this size is square root kappa minus 1. So like the size of this ellipse. But this size is actually not square root kappa minus 1, but kappa minus 1. So this is just rescale of that thing. As a result, if we drag vortex like that, we get 1 trapping distance. If we drag vortex like that, when we get much smaller trapping distance. We should multiply trapping distance by the jump, and that's how the jump behaves. It's proportional to kappa minus 1 square. We actually have to integrate all the jumps here, but which roughly would means multiply this or that by the jump. As a result, we obtain this new critical exponent. So what is difference between isotropic and anisotropic center is that this onset, you see that we're here and then it's jump, and this gives to a new behavior close to that set of strong pinning. Now, one question is, if we take anisotropy to 0, how we go from these ellipses to a ring? So for this one can consider weakly anisotropic effect where epsilon is small, so it's almost ellipse, which is almost circle. And then the onset will start at this point. That's just when we start, but then these ellipses grow, form crescent, and crescent merge, and this merging appears at another strength if onset starts at kappa equal 1, then at kappa equal 1 plus epsilon square, which is a little bit different from 1 if epsilon is small. So this crescent very quickly go to half moon and merge here. And then we recover isotropic thing. So, and this process, if we have very, well, anisotropy is very small, this process of merging ellipses to a ring will be very fast. And at merging, merging of the branches corresponds to, not to minima, but to a saddle. And close to saddle we solve and we get not ellipse but hyperbola. If we go across here, we jump from jumping hyperbola to landing hyperbola. When they merge, there is reconnection, and then we jump from here to here. So this was for uniaxial defect, but we can, in general, we may have egg-type defect with dipolar, where left and right are different. And that's how it's evolved. Then this ellipse goes to crescent, and then the merging would be in a single point. So now, if it's not a single defect, but more complicated thing, so like this, then we have complicated situation, and looks rather horrible. This actually only three anisotropic defects. So it's not some random, it's just 3 defects. But when we go, you see, we have here appears ellipses, another, now they start to merge here, and so on. So this would be situation for 2 defects. So this is just 2 defects, and it's not much simpler than before. There are again something like ellipses which are merging, and some complicated landscape appears. So these are different stages. We change effective strength or elasticity. So we have onset, then there are ellipses, so they are merging here through these red crosses are saddles, and so on. It's interesting what happens at merging. So at every merging, we either decrease the number of unstable components by 1. When 2 ellipses merge to 1, we get 1 instead of 2, so the number of components changed by 1 decreases. Or if we have merging of half of ring to a ring, the number of components is not changed, but we get the number of holes which increases by 1. So either we decrease the number of components by 1, or we increase the number of holes by 1. And as a result, what changed by 1 is the difference between number of components minus number of holes. It is called Euler characteristics. You will know why a bit later. And this changed by 1. So these are different pictures. So here we have 3 ellipses. Well, what we call ellipses, 3 pieces, 3 components, no holes. Difference is 3. 1 merging appears. Number of components is reduced. So another merging appears, another number of components. And here we have merging, number of components is unchanged, but number of holes is increased. So why this C minus H we call Euler characteristics? Actually, Euler characteristic is known from graph theory, or actually polyhedra. For polyhedra, there is Euler formula which tells that the number of vertices minus number of edges plus number of faces is equal to 2. If we look on the graph, we open one face of the polyhedra, then the number of vertices minus number of edges plus the number of faces would be equal to 1. If we have several disconnected graphs, then it would be the number of disconnected graphs. So here we have, now what are graphs for us? We take minima, and minima were associated with vertices. Saddle, each saddle connects minima, and we put edge, this red line, it's edge, which corresponds to a saddle. And when we have smallest closed ring of saddle, it gives us phase, and that's how this Euler formula works. So what is the relation between this graph theory and this? Well, first of all, we know that vortices are minima of this lowest eigenvalue. Saddles, well, edges are saddles of eigenvalue, but we don't know what is phase. And this brings us to topology, or more precisely, Morse theory, which is one piece of differential topology, well, which was done by Marston Morse, like in last century. Actually, Maxwell worked on similar problem 100 years before when he studied property of topographic surface. So the main result of Morse theory is this formula, where chi of the manifold is given by the sum of Betti number. Well, Betti is another mathematician, so Betti numbers are given by the dimension of rank of the homology, ith homology group. Well, loosely speaking, B0 means the number of components, B1 is the number of holes, and all other Betti number for two-dimensional non-oriented surface are absent, so this thing is simply C minus H. And this relates to the number of critical points of the surface with index I, and index I is the number of negative eigenvalue of Hessian. So C0 means that there is no negative eigenvalues, which means that it's minima. C1 means that it's one minima, one maxima is saddle. C2 is maxima. So plugging it here, we get this formula, which means that actually what is phase corresponds to the holes plus maxima. And we'll kind of study our manifold, which should be below 0 for instability, which corresponds to some island, well, as the place where we are, and like this minima and maxima. So the holes which we have here, they correspond in kind of the old thing to a pinned branch, and as we see, there seems to be topological invariance, and all the things we can map to effective first-order transition of Landau type. So now the last part is another useful thing, which goes back from topology, and if you remember this plot, this was the difference between symmetric and between symmetric and asymmetric branches. So I put here that we don't know what is free and what is pinned. Now we drag vortex from left to right, and then here we have these two jumps, this and that. And when it's asymmetric, we have this one jump. Now let's switch direction and move vortex from right to left. Then here, instead of jumps here and here, we have jump here and here. But the sum of these jumps is the same. The curve picture is completely symmetric. So this jumps goes to here, this jumps goes to here. So pinning force dragging here and back is the same. Now if we have an isotropic center, then before we have jump here, which was big. Now we have jump here, which is small, which means that the force, pinning force in the opposite direction is different. So it's like friction that you here it slides good, and the opposite direction it has large friction, which well people used for cross-country skiing or other activities. So which means that we have so-called ratchet. When we switch direction of apply current, we get different voltage, and we may get rectification of the signal, so-called superconducting diode effect. And this type of behavior was actually observed at Argonne, where they introduced nanoholes or nanorods. So these are anisotropic pinning centers, and well, they produce this superconducting diode effect. Well, how useful it is for modern electronics we can discuss separately. So with this, I want to conclude. So the formalism which we'll use is Hessian matrix. Apart from nice topology, we see the change in critical exponent from 2 to 5/2 at the onset of critical, and one has superconducting diode effect. For this case, of course, these defects should not be randomly oriented. If they are kind of randomly oriented, then this would be averaged out. Thank you for your attention.
You showed that the anisotropy actually wipes away the first order jump.
Well, it was an example. It doesn't have to.
It doesn't have to. Right?
If you have little, well, this jump, it was one-dimensional situation. So in two-dimensional situation, there was this picture where two ellipses appears, and then now in one dimension, if you may have different, well, in 1D, anisotropy means asymmetry, left-right asymmetry. Sure. So if you have left-right asymmetry, then in general, two jumps will appear at different and different strengths.
Yeah, okay, but you need a certain strength in order for one jump to disappear, as you showed, right?
No, if you have in generic anisotropic situation, well, jump appears at the point of maximal negative second derivative of potential. So if you have not symmetric potential, then there is no reason why left maximum and right maximum of second derivative should be the same.
Sure.
Yeah. So it would be only some coincidence, well, if it's not dictated by symmetry. Now, of course, if you make a little bit asymmetric, then these two